Good day, everybody, depending on where you are in the world. We are happy to see you here again. I think most of you are familiar with the format of this event because you have been regular attendees. But for those of you who are new, we are going to have two talks. A talk by main PI for 30 minutes, followed by 10 minutes of questions, and then a talk by graduate student or postdoc for 15 minutes, followed by 5 minutes of questions. And bringing to our attention any interesting speakers for both our main PI talks as well as student and postdoc talks. And please, in particular, the PIs who are on this call, please feel free to contact us and nominate your excellent graduate students and postdocs who have a nice story to tell. If you are a graduate student and postdoc yourself, we accept self-nominations as well. So just shoot us an email with your CV, and we will be happy to work with you to find a good time for you to basically tell your story to the community. For the rest of the year, we more or less plan to have 2 events per month, which will be the last 2 Fridays. During the month of May, we will only have 1, however. The last Friday of May, right before the Memorial Weekend, from previous year in attendance because of the end of the semester and the first summer holidays, and because of that, we just want to give us a break. So after our event on May 19, the next set of events will be in the month of June. So today we have the pleasure of having 2 very fantastic speakers. Our main speaker is Professor Barış Coşkunüzer, who is a professor of mathematics at University of Texas, Dallas. Barış obtained his PhD in Princeton, from Princeton in 2004. He then had positions at Yale, Koç University in Turkey, MIT, and Boston College before moving to UTD. And he's generally working in the area of topology and machine learning, and he's going to talk to us. And our second speaker is Dr. Shuwen from MIT. She is in Professor Heather Kulik's group. Shuwen obtained her undergraduate degree from University of Alabama in 2016. Then she did a PhD at Princeton with our own Thanos Panagitopoulos. And then she moved to MIT to do a postdoc with Heather, and she will start her own group at Cornell this July. And she will be talking about designing molecular coordination environments for selective ion bonding. As I said, our next event will be I think the date is wrong. It should be May 19. It will be 3 Fridays from now on May 19 with Professor Giorgia Brancolini from CNR in Italy and Dr. Jae Hook Jin from Colombia. And just stay tuned to receive the registration. With this, I would like to end, and without further ado, I would like to give the floor to Professor Coşkunüzer to talk to us about drug discovery using machine learning. So, Barış, the floor is yours.
Thank you very much for the invitation and this opportunity. So I'm going to talk about drug discovery by using topological data analysis and topological machine learning, let's say. Let me give a couple of remarks here. So this is a collaboration with Andaç, Demir, Ignacio Dominguez, Yushu Chen, Yulia Gel, and Bülent Kızıltan. Andaç and Bülent are in Novartis, and this work was supported by NSF and Simons Foundation. And the details are in this paper. You can find this link in my webpage. And so I assume most of you are already familiar with the drug discovery, so I'm going to give a short recap for that, and then I'm going to spend more time about the topological methods and fingerprinting methods. So the drug discovery process can be summarized in this picture. So you want to find a drug for some disease or some other problem, and you know you want to interact with some protein, and you want to find some small compounds to interact with it. You have a very large library of like millions of compounds, but your problem is at hand, and you need to address. You have limited resources. In the first step, you want to find the best compounds, so that in the high throughput screening in the wet lab, you can spend years of time on this potential compound. So the first part here is called virtual screening. By using computers and other methods, you want to find the best compounds you want to work with, like 100, 200 best ones. And then you get to this 5, 10 compounds likely to work with your protein. And then when you find them, you just optimize these compounds to make a drug. And the process does not end here. You want to show that it's really working and it doesn't have side effects. It takes 10, 15 years and millions to billions of dollars. If you are lucky, if it works, it's a very rewarding process, but it's very expensive, as you can guess. After the second step, lots of clinicians are working here, and lots of chemists are working here. So the first step, if you start right, detecting these potential compounds, you are in a very good shape. Otherwise, this whole process can be in vain. So the first part is called virtual screening, and today I'm going to talk about that part. So there are basically 2 methods for virtual screening. You give me like 100,000 compounds, and I'm going to give you the best 100 of them, like 200 of them, so that you can work with. I mean, how am I going to eliminate them? There are structure-based methods and ligand-based methods. In this talk, we are only using ligand-based methods, but let me tell you the story here. You know that you have a protein, and the proteins are working with these gaps and cavities in their structure, and they are binding the other enzymes and cells, etc., and they are preventing some functions in your bodies. And so you want to close, you want to prevent them, these proteins doing this job, by closing this gap, by filling this gap with small compounds. You want some small compounds to bind there so that it cannot attach themselves to the other enzymes or other cells. So basically, we are playing some puzzle, Lego puzzle. We are trying to fill these gaps with the right compounds. And there are lots of ways to do that. But structure-based methods basically tells us, you know the target protein here, and you know which gap is the problem, active area, and you understand the 3-dimensional shape of this protein, the gap, and then you want to fill this guy with a small compound, the 3-dimensional shape, so that it's going to attach itself to that and it's going to stay there so that it cannot function. This is called structure-based methods. This is computationally very expensive. I'm going to explain why it's, if you are going to search for large compound library, structure-based methods is not very nice because of the computational problems. Ligand-based methods is something else. We are cheating basically here. You give me the compound, but I am not interested in the target. You give me some compounds, like star-shaped compounds like this, and you tell me these guys are working somehow. It's not going to be drug, but it is attaching themselves, and they are active for this protein. So you are giving some 3 samples, 10 samples, 100 samples likely to work for this protein, and you call them active compounds. And I am using this 10, 15 compounds, and then I'm in your library, 100,000 of compounds. I'm finding the best ones which are shape-wise similar to them. This is basically for us from machine learning perspective, similarity-based search. I am doing the most similar objects, similar to my active ligands. So in this talk, I'm only talking about ligand-based methods. You give me some active compounds for your protein, and I'm going to find the best ones similar to them. So related work. So usually you want to use machines here, machine learning here. I give you compounds, you cannot fit them into machine. So what we are going to do is you give me a compound, and I'm going to give you a vector, so that your machine is going to take these vectors, and these vectors are going to represent some molecular structures of some common structures in your molecule, and then it tells me what kind of substructures it has, and then I'm going to look at them as vectors. So you give me 100,000 components. I'm going to vectorize them. I'm going to embed them in the 100-dimensional space. So in the 100-dimensional space, you have 100,000 points. And you are going to tell me that 50 of them are nice guys, active components. I'm going to find this 50 fingerprints, 50 vectors in my 100-dimensional space, and I'm going to find the nearby ones. So there are two common methods so far. The last of common methods, most common ones are Morgan fingerprints and smiles, one-dimensional ones. In the Morgan fingerprints, this is basically in graph representation we're learning correspond to Weisweiler-Lehmann algorithm. Let me tell you about this. Let's say this is representing a compound or some graph. The nodes are atoms and bonds are edges. What I start with is I have like 3 A's and 2 B's here. And I'm looking at the one neighborhood of that. So let's take this B here. In the neighborhood of B, I see 1 B and 1 AB. A and B are here. I am gonna mark this up. For this guy, I see B in the center and 2 A's and B. So for each structure you see, this can be carbons, hydrogens, etc. You are using some hash values. This is a very common method in computer science. For every structure, these are called multisets for us. And for every structure you see here, you just randomly give me a 16-digit number. But whenever I see this BAAB, I give you the same 16-digit number. This is called hashing. So 16-digit number for every structure you see here, you are just labeling them as some hashing values. And then, for example, for every compound, you want to get 1,000 dimensional vector, 1,024 dimensional usually. And this 16-digit number is divided by this 1,024, and the remainder, let's say 755. Now, you start with 1,024 dimensional vector, all zeros, and you activate this 755 to be 1. And then you do it for every substructure you see here. You have like lots of hash values. You divide them and then you activate the corresponding guys. This looks very dummy method, but it works very well in computer-aided drug design, because for every molecule, somehow you encode the substructure information in this binary vector, and you give me a 1,000 dimensional vector for every molecule. This is called Morgan fingerprinting. The other one is called smiles. This is a reversible. The first one, the Morgan, is not reversible process. I give you the vector, you cannot give me the molecule, but this is a reversible process. That's nice, but this is very unstable in the sense that these two molecules here, for every molecule, I give you some string like this. CC1 and numbers and parentheses and some other signs. For every molecule, I can give you one-dimensional string like this. You can call them as a vector. But the problem here is if you make a small change in the molecule here, they are very similar still, but the representations can be very different from each other. That's why similarity search is very hard with the smiles method. Three-dimensional methods, for every object, for every compound, you give me three-dimensional picture of this, and then you can give me two compounds and you can fit them, align them, and then you can say they are very similar to each other or not. This is also computationally very heavy, because for every molecule you give me, you are going to give me some three-dimensional picture of it, and then to see that two different compounds are similar to each other, you need to look at all rotations, all translations, etc., and see if they are fitting to each other or not. These are ligand-based methods. And we are going to use topology in this one. So we are going to make a fingerprint. We are going to produce a fingerprinting method by using persistent homology. But let me give you some background in homology here. So if you are not very familiar with this, you are just going to look at the following pictures. So when I say zero-dimensional topological feature, I am just looking at the number of components here. How many pieces my space is. Here you see 1, 2, 3, 4, 5, 6 pieces. I am going to say zero-dimensional homology has rank 6. I have 6 pieces. Zero-dimensional topological feature is rank 6. One-dimensional is number of holes, number of loops, essential loops you have in your space. For example, here you have 1, 2, 3 loops. My one-dimensional homology is rank 3, and I have only one component. This is just one piece. So zero-dimensional rank homology is just rank 1. Let's look at the orange, the brown region here. I have only one piece. They are all connected. So the zero-dimensional homology is 1. Now I'm going to count the holes here, in the loops here. So I see one loop here, one loop here, one loop here. I have 6 loops. Now question, I have a triangle here. This is also a loop, but it's a fake loop for me because it's filled. I am not going to count them as a loop unless it's not filled. So if it's filled, I am not counting them. So these guys are essential loops. I am only counting the loops here. For if you want to go further, two-dimensional homology is the following. If you have a sphere and the void inside of it is a two-dimensional topological features, in the two-dimensional homology, I am counting the cavities in my space. Holes are one-dimensional features, components are zero-dimensional features, and two-dimensional features are the cavities and voids in my space. By the way, if you have any questions, just please feel free to interrupt me. I'd be happy to answer your questions. So I'm just gonna give you lots of pictures and examples, but basically, persistence homology works in the following way. It's a 3-step process. You give me data, or in general, any data like point cloud, graphs, or any images. What I do is I produce this sequence of topological spaces out of it. I'm going to give you some examples in a minute. In this sequence of topological spaces, I am looking at the evolution of these topological features, zero-dimensional features, one-dimensional features, or two-dimensional features. I am just looking at in my first element, in the first topological space, do I have these guys or not? Second one, it is continuing to survive, etc. I'm going to give you some examples, and I'm recording them as a persistent diagram. So you give me data, I produce a filtration, a sequence of topological spaces. I record the evolution of these topological features as persistent diagram. Persistent diagrams are not very useful for machine learning purposes. I'm just going to give you vectors out of it, meaningfully representing my persistent diagrams. That's the main story for TDA in 1 minute. But let me give you the intuition here. So I give you 2-point class like this. You can imagine them like these are atoms in the space, atomic coordinates of the 3-dimensional coordinates of atoms, or some point cloud, or any data you have is a point cloud. And you see some patterns here. You cannot name it, but you see in the left one, you have 2 small circles. In the right one, you have 1 big circle. And you can see that the one big circle has a dense set of points that are very close to each other. In the left one, you don't have the same features. So you have 2 loops in the left, you see 1 loop in the left, but how are you going to name it? So we want to get some, we have this intuition, data, this point cloud comes with some shape patterns, but we want to formally record them so that we can use for machine learning purposes. So let me give you a very simple example how we are doing this. So for point clouds, what we do is the following. So you give me a set of points like this. You see 15 different pieces. Okay. You see 15 different pieces here. So I have 15 components. Red ones will represent my zero-dimensional features. So I start increasing the radius of the disks here. So I am building some union of disks here, as you can see. So at the center of these points, 0.1 radius disks, union of it, 0.2 radius disk, 0.3, and I am increasing the radius of the disk, and I am seeing the topological patterns change in the topological patterns here. For example, at 0.5, I see 1 component here, second component. All these guys merged. I have only 3 components, 1 component here and 1 component here. You see, you have 5 components left. You start with 15 guys, you start increasing the radius of the disks, and you see here 0.3, 5 of them merged, and then you come to 0.5, only 5 of them surviving. When you get to 0.8, all of them merge to 1 component. And this barcode here starts at 0 and lives forever, these red barcodes. So this is my zero-dimensional persistent diagram, basically. And 1 dimension, I am checking the loops here. I don't see any loops here yet, any holes. But when I hit 0.7, for example, this big loop emerged. I'm going to mark it down. There is a hole in my space. And I am still increasing my radius. And when I hit 0.9, this small loop also emerged here. I am marking them down. I am increasing my radius. When I hit 1.3, I see that this small loop disappears. So the birth time for my small loop is 0.9, the death time is 1.3. And I continue here, and I get this barcode. The big one is dying at 2.5. I have barcodes here. I start with 15 red bars here, and some of them are died along the way, and 0.9, 0.7, all of them died except one. For one-dimensional barcode, I have two loops. One of them is born at 0.7 and died at 2.5. The other one was born at 0.9 and 1.3. So you can look at it as a barcode like this, or you can convert just initial points and end points in this diagram. This is also called persistent diagram. Now, this is for three-dimensional point class, but we are more interested in, so I told you about the filtration. You give me the point cloud, I give you a sequence of topological spaces, this yellow guys. I just kept track the evolution of the topological features like that and record them as a persistent diagram. This is the main idea in topological data analysis, persistent homology. But my main question is going to be for graphs. For each graph, there is a natural way to induce a simplicial complex in the following way. You give me a graph. Whenever you see a triangle, you fill them up with a triangle. Whenever you see a four-click, which means you have 4 points, they are all connected to each other. We call them four-click. You are filling this with a tetrahedron. And if you have like 5 points connected to each other, you are filling with a four-dimensional simplex. You get a topological space like that. So for example, I have a graph like this, and I am giving some function values to each node. This node goes to 1, this node goes to 2. This is a very random function. Usually we are taking meaningful functions for the coming from the domain. And in our case, our molecules will be graphs, and our node functions are atomic mass and partial charge and the bond strength. So here, the way I could build this sequence of topological space is the following way. I give a number to, I define a value for each node. I am start activating them when the return comes. For example, when I hit value 9, I start from 1. I activate all the nodes whose value is smaller than or equal to 9. 1, 2, 3, 4, 5, 6, 7, 8, and 9. You see, I get this subgraph. This is G9. And I am looking at the topological space here. Now I am activating 10th node. And I am adding this node here. I get a new subgraph. And I keep continuing. I am activating 11. And I get a sequence like this. Now I'm going to keep track of the changes in this filtration. And then I'll go get some signature out of it. That's the basic idea. I'll give you lots of examples about that. Now, when you get the persistent diagram, it's not very useful for machine learning purposes. We are getting some functions out of it. So the simplest functions we use is beta function. How many topological features I have in a given threshold? Between 0 and 1, I have only 2 surviving topological features. I am marking it 2. 1 and 2 is 3. 2 and 3, between 2 and 3, I have only 3, and I continue like that. I just count how many topological features do I have in a given threshold. So for every data you give me, I give you a function like this. You can call them as a vector, 7-dimensional vector, or a function like this. Now, in the multi-parameter persistence, instead of using one function, I am using 2 functions. This is something new. In the last 3-4 years, this persistent homology is getting high attention, and the multi-parameter persistence is working well. And what we do is we are using 2 functions to filter our molecules or data here. Okay, so before starting about describing my fingerprints, let me give you why we are doing 2-dimensional model but not 3-dimensional model. This is very important. Usually as a topologist, I want to go with the three-dimensional models because there are much more information there, of course. But unfortunately, in the compounds, we have this conformation problem. You give me like 100,000 compounds, but for each compound, for single bonds, when you rotate them, they get a different shape, different three-dimensional coordinates for every atom here. So the shape changes. Every conformation is a new molecule for me. Even though they are the same molecule, they are just isomers for each other, but this is a different shape. It's a new candidate for me. So I cannot count them as same guys. So 100,000 compounds you give me, because of the conformation problem, I have to compute their conformations and etc. It's a very difficult to use three-dimensional model here. Instead, I'm going to go two-dimensional in the following way. So you give me a compound. I represent them as a graph. Every atom is a node. Every bond is an edge. And then I use important chemical quantities in my filtering functions, node functions and edge functions. In this work, we use atomic number of each atom, partial charges, and bond strengths. There are 4 bond strengths: single bond, double bond, triple bond, and aromatic bond. Aromatic is the highest level, 1, 2, 3, 4 level of filtration here. So I know some of you are lost already because of this topological background, but just bear with me because I'm going to give you lots of pictures in the following slides. You give me a cytosine, very small compound, and I'm going to give you a topological fingerprint, a matrix out of it in the following way. So white ones are hydrogens, gray ones are carbons, blue ones are nitrogens, and red one is an oxygen. Okay, so one I am going to give you a bifiltration out of it in the following way. So you can think of this as I am decomposing the whole molecule into substructures in an organized way, basically. You give me 100,000 compounds. For each one of them, I am using the same thresholds, and I am comparing their corresponding substructures out of it. How am I going to do that? Let's look at this box. So I am activating every node, every atom whose partial charge is smaller than 0.3 and whose atomic number is smaller than 7. I am activating every node whose partial charge is smaller than 0.3 and atomic number is smaller than 7. I got these nodes, and if there is an edge between them in my graph, I am activating them too. So I get 4 by 4 substructures starting from here, and I have 16 substructures in an organized way like this. Usually what we did is 10 by 10 or 10 by 20, 10 thresholds for atomic numbers, 20 thresholds for the partial charge, etc. What we have here is a decomposition of the whole substructures. Now, I am going to give you some numbers out of it. So you can describe your numbering here itself, but what we did is a topological data analysis is usual tools are homology. I can call them number of compounds for each substructure or number of loops for each substructure. You can go, so for this one, I have 3 components, 5 components, 4 components, 1 component. How many loops do I have? 0, 0, and only here, these two have 1 components. These are giving some nice matrices out of it. There is one non-trivial way to do this. I'm skipping lots of the details here, but I want you to see this too. I cannot use 3-dimensional model because of this conformation problem, but I want to still care about the distances of this atoms here. When I have my filtration, I can still do the following. So I am just looking at the graph distance between them. So this node and this node, for example, have distance 4, 1, 2, 3, 4. I'm going to record them as the following. You give me a filtration, and I'm going to do another filtration in the other direction in the following way. In the first column, I don't do anything. In the second column, if there is the distance between the 2 nodes is equal to 2, I am putting an edge between them. If in the third column, if the distance between the 2 nodes is equal to 3, I am putting an edge between them. So the dark edges are distance 2 edges, distance 3 edges, and red ones are distance 4 edges. It gives me a different filtration, and it will tell me the graph distances between the nodes in the substructures I am having here. So basically, this is how I get my matrices. For every molecule you give me, I'm going to give you n by n matrix. Basically, m thresholds for my partial charge and thresholds for my atomic number, for example. It gives me n by n bifiltration. For each one of them, you can count the number of loops, or you can use some different chemical quantities for these substructures you are having, and you get some number out of it for each box here. And then this is going to give you a matrix. And having a matrix is a very important here, not just a simple vector. I'm going to come back to that. Now, our experiments gave us a very good result with this fingerprinting method. So we use two different data sets. One of them is a very small one. The other one is a very large one. Basically, large one. These are both benchmark data sets. The small one is important because most of the time you won't have many ligands. So the cleavage chain data set has 22 targets, and for each protein target, it gives you 2 or 3 training samples, and it tells you to find the remaining active compounds out of 850 decoys. For example, for F, you give me 2 active compounds and I'm trying to find 4 active compounds out of 854 compounds here. In the .E diverse data set, I have 100,000 compounds this time. I have 8 targets. And in this one, for example, I have 62 active compound and 2,900. Usually we take like 10% of or 5% of the active compounds for our training set, and then we want to find the other remaining ones. It's already described in the .E diverse data set. But how are we gonna measure our performance? We are not interested in the whole accuracy. We are only interested in our best cases are good or not. So, for example, 1% enrichment factor. This is called enrichment factor. What we are going to do is, so if you don't do anything, your random chance is number of inactives over n total. So you build a model and you give me the ranking. You give me your best 10 guesses or best 20 guesses. Out of this best 20 guesses, how many of them are real hit? You are only interested in this measure here. So how much do you enrich the random chance, basically? So your model is how much does it enriching your random chance? And 1% enrichment factor means out of, so if I give you like 1,000 compounds, your best 10 guesses, 1% of it, how many of them are hit and how much do I enrich your factor here? So enrichment factor for 2% can be at most 50. I can enrich at most 50 times. Enrichment factor for 1% is at most 100. So out of this measure in the cleavage gene, so these are all recent models here in this small data set. So we are almost doubling in every target here. So we get like relative gains 90%, 80% in the all these deep learning and machine learning models here. Now I want to make a quick comment here. We have 2 models. One of them is using random forest. You give me fingerprints, I use random forest. This is a very standard machine learning model. The second one is very important. We are using deep learning here. Convolutional neural networks, vision transformers here. And if you look at this fingerprint, this is an n by n matrix. You can consider, if it's like 10 by 20 matrix, you can consider it as a 200 dimensional vector, or you can consider 10 by 20 matrix. This is very important in the sense that if you look at them as a 10 by 20 dimensional matrix, this is considered as an image. That means the location of the entries are very important. So this guy is related to this guy is related to this guy because they are coming from the filtration. The substructure here and substructure, how is it changing is important. And convolutional neural networks are basically doing this. In this small data set, it is very important because you are doing few-shot learning, because you are giving me only 2 components which are active here. You don't give me like 100 compounds which are active. You give me like 1 or 2 or 3 compounds, active compounds, and you are trying to find the other ones, you can think of, I have 1,000 compounds and I'm telling you 2 of them are good. In the 100-dimensional space, you have 1,000 points and you are marking 2 of them as red and find the other guys closer to this red guys. It's a very hard problem. But vision transformers are working very well because you can customize your goal in your vision transformers in the deep learning methods by defining your loss function, and it worked very well here. In the other one, random forest worked very well. So these are all using graph neural networks or deep learning methods in the last 2-3 years. We are getting like 50%, 30%, 40% gains, relative gains, or most of them in the range enrichment factors. These are all 1% enrichment factor scores, and we are getting very good results here. So am I over time? Oh, okay, let me finish with this. So these are some filtration methods we are using. We use atomic mass and distance here, partial charge and distance, bond type and distance, atomic mass, partial charge and distance, all modalities, atomic mass, partial charge, bond, and no distance here. We get very good results depending on the target here. So not one model works best for each target. Depending on the target, the filtration function is changing. Oh, okay, let me finish with this. So what is next? You can look at ultra large libraries because we have a very computational efficient method. You give me a compound, I give you a matrix. And it's customizable because I use only atomic number, partial charge, and bond strength, but there might be much better functions to use in your graphs, and you can use them with our method. There are other multiprocessing methods. I didn't go into that detail. And as a few-shot learning problem, this is a very good example. And another problem we can look at here, not classification problem, but you can look at also regression problem, molecular property prediction. So you give me a compound, I'll give you a score out of it by looking at the working compounds and how similar they are to the working compounds with this method. Because this, at the end of the day, I am doing a fingerprinting, and after that, it's all machine learning. I can use this fingerprints for classification problem or regression problem. So you have to customize your loss function, but you can also use this model for molecular property prediction. I am sorry, I'm already over time, so thank you very much for attention. And if you have any questions, yeah. I'll stop.
Thanks, Barış. Sorry, I had to. I have some internet connectivity issues, so I had to join through my phone. That's why it took a bit longer for me to unmute. So thanks, Barış, for the wonderful talk. And so we can open the floor to questions. So if you have any questions, I mean, raise your hand, and you can just. It looks like we have Jake.
Yeah, thanks for the very nice talk. So whenever you're saying distance, you're talking about the graph distance, right? Not the.
Yes.
Okay, so there's no 3D considerations so far in this model? Okay.
Yeah, you are right. As a topology, when we started this problem, we started like this. We should go for the 3-dimensional, but when we learn about conformation problem, okay, so this is really hard for us because not every compound comes on conformation. You have to find their conformation yourself. And every conformation is a new molecule for me. That's the problem because it comes with a different shape. So when you change one of the single bonds, rotate them, it completely different shape. It doesn't have the same shape. So every isomer is a new compound for me. And instead of that, we just go with the 2-dimensional model, graph representation, and we use the graph distance basically.
Yeah, okay, so this is not doing binding affinities yet, right?
No.
Okay, thank you.
Unfortunately.
I don't see any questions. Okay, I have something in the chat. Let me see. Okay.
Sorry about that. I didn't see the.
Zach, so do you want me to ask, or do you want to?
I can ask, sure.
Yeah,
it's kind of a follow-up. It's a follow-up on the previous question. Like, if we wanted to do structure-based, could we just plug these fingerprints into a graph that already had distances in it instead of trying to rework the fingerprints?
You can do it for structure-based, but if you are going to do structure-based, it's a much finer information. I would suggest a 3-dimensional model. So
Yeah,
remember
so-
this.
Say I have a GNN that already has like a three-dimensional model. Is it worth plugging these in as additional features?
Oh, yes,
Or-
yes. That's a very good question. So I'm highly interested in graph representation learning too. So topological data analysis gives you a different features extraction method. So this is completely different method. So you get a 100-dimensional vector out of nowhere, and it's a very useful information. GNNs are looking at fine neighborhood information. In the first part of GNN, you are also doing some feature extraction.
Mhm.
The second part is MLP feed-forward part. In that part, if you can integrate your TDA features to your model, you might get a better result. And there are lots of examples of combining TDA with GNNs, so you can check them up. They are trying to integrate this very variable feature extraction methods to get a better result, to get more robust results and better results in this sense. Yeah.
Okay, cool. Thank you.
Mhm.
Hi, I have quick
Mhm.
question. Sorry, I'm a little bit confused between those two slides where you show the I think two-dimensional featurization scheme, partial charge versus atomic number, and the next one about the distance. Yeah, so
Yeah.
are they two?
They are not related. They are not related. So this is sub-level filtration, very simple filtration, this one. I am only considering there is no distance here. I am just decomposing my molecule into substructures by just looking at these values, and it's a subset here. Now I am adding new edges here. This is distance. We call them biatory strips. This is high technology for graph representation learning. So this is considering graph distances here. As you can see, the original graph appears in here, upper left. In the right ones, I am adding new edges to my original graph. In this one, I am not adding any new edges. I am just decomposing the existing nodes and edges. There is no new edge here. So what is the advantage here? I see that, for example, in the look at the lowest row, I see I have only two nodes. They are disconnected. Disconnected here, and they become connected in here. That tells me these two nodes have distance 4. So I get the distance information out of this with this fingerprinting method. But you can use 3 or 4 functions like this at the same time. So you don't want to go too many dimensions, because you are losing, you don't get too much information out of it. You are just correlated information here. So we are just having either 1 functional distance or 2 functional distance here in our model.
So ultimately, when you're constructing the metrics that you showed earlier, are you using this scheme?
So no, it's here. So we use like different models: atomic mass and distance, partial charge and distance, bond type and distance, atomic mass, partial charge and distance. This is a 3-dimensional array now. It's not a matrix. You have 3 dimensions now. Or all modalities: atomic mass, partial charge, and bond type. We don't have distance here. This is also 3-dimensional.
Oh, okay. All right. Thank you.
And by the way, if you wanna go in this direction, so we are topologists, we don't know much chemistry. So imagine you are doing this decomposition. So in our experiments for graph classification, the most important part is constructing this filtration first. And out of these substructures, you might name a different number out of it. For example, we use components 2, 4, 3, 1 here, but you might use some more clever version of these chemical quantities for these substructures. That will give you a different fingerprinting method, definitely. But the main idea is using filtrations, decomposing the whole molecule into substructures like this in an organized way. You will do this for every molecule so that you can compare the substructures between them.
Thank you so much for the explanation. And one more thing, like so I noticed, I mean, you mentioned that you use the either Bayesian transformer or the convolution-based model, partially because you constructed the image like the metrics. But I was wondering if it affects any performance if you increase, say, the bin size, because you are essentially kind of collecting this like information in a 2D histogram way. So does giving it a more fine bin like give you better?
Yeah, I mean, increasing the threshold does not improve too much because if you are using two-dimensional vectors like this, so 10 by 10 versus 100 by 100. So if you are looking at this image, you don't have too much information in the 100 by 100, and you are making your machine learning model works harder. But there are some optimal numbers here. You can find it with experiments. In our one, 10 by 20 or something like that, if we go to resolution more than 200, we don't get much information out of it. And if you are using 3D, you should choose smaller numbers for threshold for each dimension, because you don't want to get like 1,000 dimensional vector with less information.
Yeah, right.
So let's move on. Sorry, let's move on to the next question, because we are running out of time. So you have two more questions, and then we can just move on to the next speaker. So I have a question from Mehmet Aktaş, who asks, did you consider using higher dimensional persistent diagrams, such as dimensions greater than 1?
No, I mean, this is a very good question. If I use a three-dimensional model like this, point clouds, the most important dimension would be two-dimensional. You are right. But I am using graph model. So that's why we didn't go to two-dimensional. We only go 0 and 1 dimension here. But if you are using three-dimensional atomic coordinates of the compound, then you should definitely use two-dimensional information. That's it. Yeah, it's an important question. Yes, thank you.
So we have Masroor who has a question. Maybe you can quickly unmute and ask the last question.
Hi, thanks. I have a general question. So you talked about Morgan fingerprints.
Yeah.
Like you maybe 1024 or 2048 Morgan fingerprints. But how do you find the optimal number of Morgan fingerprints for a particular data set?
I mean, you don't, but usually 1024 or 2048 is used. So 2 to the 8 to 2 to the 10 is here. But the thing is, you never know, but most common use is 1024. That's why I said 1024, because if you go higher, you are going to get lots of zeros in your vector, but you always get some hash value, 16-digit number, and the remainder of this will give you some activating this number, these zeros. So it's completed a dummy process in a way, but it works very well because it captures substructure information you are having in your compounds.
Okay, thanks.
But there is no rule for this. You can go for like 1,000, 512, but usually 1,000 is a common number used in this domain.
Okay, thank you.
Okay, so I guess we can thank Professor Coşkunüzer one more time and applaud him, and then we can move on to the next talk by Shuwen. So Shuwen, the floor is yours.
Thank you.
Shuwen, you're muted.
I think you are muted, Shuwen.
Oh, thank you. Sorry.
Okay. Now we can hear you. Go ahead.
Great. Well, thanks for introducing earlier, and I really appreciate being here because I've been attending these seminars for since the pandemic times, and I think it's a really great opportunity to connect everyone in the community. So they've been certainly very helpful to me, and so I think I'm really appreciative of the opportunity to come and talk here. So as Samir introduced earlier, I'm a postdoc at MIT in chemical engineering. And today I'll be talking about designing molecular coordination environments for selective ion binding using machine learning. But before then, I'm going to just hijack the first couple minutes of this talk and just plug a couple of things. So the first is I'm starting a research group at Cornell in chemical engineering, working on molecular design for water and energy systems. And my group will be working at the intersection of multi-scale modeling, both classically and quantum scale, chemical informatics and machine learning to design novel electrolytes and charged fluids for energy storage and stable solvents, as well as solution material interfaces for chemical selectivity. And to do this, we're working in the areas of designing machine learning potentials and using these potentials to study interfacial phenomenon, as well as chemical reactions and solvent electrolyte effects on these reactions. We're also looking at material screening for chemical selectivity using machine learning approaches to inversely design materials for particular chemical separations. I'm recruiting at all levels, so PhD students and postdocs. For PhD students, if you're interested in any of this work, we have full admission process through the CBE department. So I encourage your excellent undergrads to apply through the regular admission cycles. And for postdocs, I encourage really outstanding candidates to apply for the prestigious Eric and Wendy Schmidt AI and Science Postdoc Fellowship. I think we're one of 4 or so universities in the US which receive this generous funding for postdocs to specifically work at the intersection of AI and chemical sciences. So if you're interested in any of these opportunities, please reach out to me. My email is here. And the other announcement I want to make is that the GRC Chemistry and Physics of Liquids is happening this summer. And the StatMech community usually has a pretty strong presence at this conference historically. So I just want to encourage everyone to look into it and apply, particularly for students and postdocs. We have the GRS preceding the GRC, which I'm co-chairing. And this is just a short 2-day conference for just students and postdocs to have an opportunity to network and ask a lot of questions at the talks. And everyone has an opportunity to present a poster. Both of our amazing STMS organizers, Sapna and Amir, are both invited speakers and they'll be attending. So if you wanted to meet them in person, you should apply. So deadlines are early July. Okay, so let me get into the science. So as I mentioned earlier, I'm working on designing molecular coordination environments for selective ion binding using machine learning. So this is what I've been working on during my postdoc. So why do we want to design these coordination environments for ion binding? Well, the main application is for desalination membranes. And in membrane design, there usually are 2 key aspects of assessing performance, selectivity and permeability. And when we want to apply a flux of fluid across a membrane, we wanted to singularly select a specific set of species while rejecting others. So we want as much of that species to pass through as possible in a given amount of time. So usually there's a trade-off between these 2 criteria. And in desalination membranes in particular, selecting certain alkali metal ions from others is pretty challenging. So your potassium or sodium, lithium ions are all very similarly sized. They have the same charge, very similar chemical characteristics. It turns out in biological systems, there's this very exquisite way of making these kind of separations found in potassium channels, where the selectivity of potassium over sodium is on the order of 1,000 to 1. So for every 1,000 potassium ions to pass through the channel, only 1 sodium ion does so. And none of the synthetic membranes can approach this kind of efficiency. And the way that these channels are able to do this is through a very precise structural and chemical characteristics of the selectivity channel, where when an ion leaves, so when a potassium ion leaves the coordination water shell, the distances are just so precisely the same as the channel that there's very little enthalpic penalty for this transition. Versus for the sodium ion, the distances are just ever so slightly off that there is an enthalpic penalty. And so there's this strong favorability for potassium to enter the channel over sodium. And so that's the mechanism of how this potassium channel works. And we want to kind of take inspiration from this if we can design materials to mimic this very precise structuring and coordination environment to replicate this very high selectivity. So to do this, we turn to MOFs, metal organic frameworks, which are these rigid, porous materials with a very highly tunable nature. And we can essentially decorate these channels of the pores with particular functional groups to control the pore size, as well as the chemical environment which an ion would feel passing through it. And so the total possible design space of these candidate materials, which we can optimize towards ion selectivity, is really large, even if we limit to just MOFs. And the conventional approach to experimentally probe all of these options is kind of one by one by hand, trial and error, which is quite expensive. So in our group, the GLIT group, we've developed a set of computational tools over the years to help aid with this vast design space exploration using machine learning and data-driven techniques. So I just wanted to highlight some of these tools that have been previously developed in the group. And the outcome of these tools is a way for us to find regions of the design space most optimal for purpose for, in our case, ion selectivity and permeability. So in particular, we constructed these molecular fingerprints. So it's a good introduction from the previous speaker talking about molecular fingerprints. So we have these molecular fingerprints called revised autocorrelation functions, or RACs. They're kind of like based on molecular graph, but weighted with heuristics of the atom information, for example, electronegativity or atomic number and so forth. And these fingerprints allow us to map MOF structures to their functional properties, and we can do high throughput screening with these fingerprints. We've constructed machine learning models which can determine the stability of MOFs, at what temperature it degrades at, and is it stable after you remove a solvent that the MOF is in. And then these stability models are actually made publicly available in a user-friendly web interface where experimentalists can actually add additional reports of some newly synthesized MOF and the associated stability, and essentially give you feedback on our model and make it even better. And lastly, our group has also constructed machine learning models which have these physical interpretations about which type of structural and chemical features are most informative about ion selectivity, like polarizability or electrostatics, and helps us give some fundamental knowledge to aid our understanding of the underlying design rules and driving forces behind ion selectivity. So with these tools in hand, we set out to look at how we can identify the best MOFs for the purposes of ion selectivity in desalination membranes. And our approach to this problem of materials design is a screening process of starting with a large set of experimentally accessible MOFs. So this is a database of MOFs which experimentalists have synthesized, so they're achievable through experiments. And we kind of pass it through these several criteria necessary for efficient desalination. So one aspect would be the stability of these MOFs in water. So MOFs are conventionally used for gas separation. So it's really much a question mark as to if existing synthesizable MOFs are even stable in water. So we're currently in the process of building models based on an existing water stability data set, as well as using some natural language processing tools for additional data and training a model on stability. But we previously worked on thermal and solvent removal stability. Another aspect is the electronic and structural coordination environments which ions experience when they're passing through the channel. So in particular, what kind of environments are most amenable to one species of ion, but not others, hence selectivity. And we explore this using DFT and machine learning to extract feature importance. And lastly, we also eliminate toxic metals. And then lastly, we use molecular simulations to explore transport properties of these ions, specifically molecular dynamic simulations to look at diffusion. So previously we looked at methane in these MOFs. Currently, we're now working on water and ion diffusion in these MOFs. We're actually collaborating with Amir and also Maniel Melik at Yale on this area. So today, I'll just talk about one of these criteria. I only have time to talk about one, where we're going to look at the characteristics of the pore channel coordinating environment, which is most amenable to certain ions over other ions, enhancing ion selectivity. So we can study this problem with DFT, a fully periodic study, but that would be very expensive for like a fully quantum periodic study of MOF. So we turn to a representative isolated structure of molecular cages, which we extract from the Cambridge Structural Database. So these are structures that experimentalists have synthesized and deposited. So these are, again, experimentally accessible structures that have that contain an alkali metal. So these are complexes that contain potassium, complexes that contain sodium, complexes that contain lithium. And from these molecular cages, we're hoping to gain some insight on the preferential binding environment for each ion. So we collected these three classes of structures, and we did some cleaning procedures to prepare them for DFT calculations. So our goal is to identify trends in the kinds of complexes which have high selectivity and identify what are the underlying chemical and structural features that govern these ion preference. And to answer these questions, we're calculating the differential binding energy and then building some machine learning models to obtain feature importance. I'll talk more about this in a later slide. So let me share more about the screening procedure we went through. So as I mentioned earlier, we take the CSC and pull out these complexes that have each of these unique alkali ions, and then we clean it. For example, we make sure the complexes are always in a confined environment because we want these complexes to essentially represent a confined MOF or a confined material. And then various other things like making sure their coordination are not some really anomalous structure. And then we make sure that they have user-defined charges. And then we perform geometry optimization on them. So just a quick preview of what these complexes are like, just so you have a sense of what this data set is. I'm just showing a few distributions of geometric features and electronic type features about this data set. So here I'm showing this ion coordinating atom distance, a relative distance. So you can think about it, it's basically the distance of the central ion with the coordinating element, but scaled based on the ionic distance, radii of the coordinating atoms. And so you can see that in the coordination number, and then the charges on these atoms, as well as the electrostatic potential. You can see that there's some shifts between each of these distributions based on different ions. So we hope that we can essentially make the distinguishment between these slight differences in the peaks in order to find what is distinguishing about each of these complexes that can be selective for certain ions over other ions. So we define differential binding energy as how happy a complex is when coordinated to one ion relative to another ion. So I'll show you an example. So here I have a complex of coordinated to potassium and another solvent in water, and we basically flip the presence of the two ions. So sodium to the complex and then potassium in the water. And from this stoichiometry, we can determine the difference in energy of the switch. And so we're doing geometry optimization on each of these structures. Using DFT, the B3 elliptic functional, the LABPZ star basis set, and dielectric of 10. So I do want to note that this involves this reorganization of the complex itself to each of the two complexes as we change the ion. So if we look at this differential binding energy for one of our classes of structures, so these are complexes that natively hold potassium, and then we try to change it out to sodium or change it out to a lithium. So on this axis, we're looking at if it prefers to change the lithium, and on this axis, if it prefers to change the sodium. We're moving further along. Each axis represents more unfavorability. So this parity line on this plot is just showing complexes that would equally prefer changing to sodium or lithium. In this case, we can see the set of points lie above the parity line, which represents a more favorable transition to these native of these complexes to sodium rather than lithium, since it's more unfavorable in this direction. So what if we then look at each of the different data sets, and we can just look at so previously we were just looking at this one. We can also see that this is the sodium set and this is the lithium set. You can see that these native sodium complexes similarly prefer this transition to potassium over lithium, while the native lithium complexes don't really show a strong preference to either one. So kind of that just lies along the parity line. And I should also mention that, these ions, the potassium is the largest, the sodium is the middle, and then the lithium is the smallest. And the relative sizes of these to each other, we're learning is really governing this selectivity process. So another interesting characteristic to note is that the positive correlation of these native potassium complexes and these native lithium complexes. So these native potassium complexes, the complexes which are more amenable to changing to the smaller sodium ions, are also the same complexes that are more amenable to changing to the even smaller lithium. And similarly for the native lithium complexes, the complexes which like changing to the larger sodium are also the complexes that like to change to even larger potassium. But the sodium set is actually the most interesting in that there's a negative correlation. So here are complexes which the complexes that do prefers to change to the smaller lithium ions are not the complexes that prefers to change to the larger potassium ions. So this makes sense since this opposite direction ion size change. So I do want to also note that, that we can find a few distinct structures from these sets that can tell us more about why they are particularly suitable for one type of ion. So for example, in this native potassium set, we can look at this green triangle here, which is really highly unfavorable when changing to lithium to sodium, which means it really, really likes potassium over the other two, so it has high selectivity for potassium. So this green triangle is this Lelgis complex, which has a coordinating number coordination number of 11. So 11 atoms are coordinated to this central ion. Vice versa, if we look at this complex in the green triangle here, which has strong preference to bind to lithium and not the other two, is this complex called GEM, Kev, and similarly this other one that is very similar. And this has a coordination number of 4. And if you look at the distribution of our coordinating numbers, these two complexes that have strong preference for lithium have this very small coordination number. This complex that has strong preference for potassium has a coordination number that's really far skewed on the right here. So we can say that just one trend to point out, there are many others, that these coordination numbers have a strong influence in dictating which ions are most preferable. So I've told you a little bit about the geometric picture of how these structures, for example, coordination number, can help determine what is most favorable binding. So I want to tell you a little bit more, on the other hand, electronic kind of features. So we then decompose this total binding energy that I previously mentioned to 2 components: a strain energy and a interaction energy. And the interaction energy is this enthalpic change of the energy of the ion moving in and out of the complex. And the strain energy is just this reorganization energy of the complex as it makes itself more comfortable around the new ion. And so if we look at the breakdown of these 2 types of energies that make up the total energy, we see that the majority of the contribution is this total binding energy, which is interaction-based rather than strain-based. So this enthalpic contribution is the dominant factor in determining ion preference. I also want to mention here that you can see that the larger peaks all come from this these three ion pairs where you're going from a large ion to a smaller ion. So in each of these 3 cases, large ion going to a smaller ion. And these have more of this enthalpic interaction-based energy contribution. I'll come back to this point in a little bit later, so I just wanted to make a note of it now. So next, we decided to take these binding energies and train a machine learning model and try to identify what are important features that govern the selectivity phenomenon. So we tried several different models. Ultimately, we landed on a KRR model, which performed the best. So we trained a KRR model with a recursive feature elimination and just defined some physically intuitive features that can tell us something meaningful about the picture of the coordinating environment. So they're divided into 2 categories. So geometric feature, for example, the coordinating distances of the coordinating atoms to the central metal atom, as well as RMSD, so basically things that involve the geometry of the structure. The other hand, we have electronic type features, for example, the identity of the coordinating atom elements. For example, here are all oxygen atoms, carbonyl groups, kind of coordinating to this, and also the charge of the coordinating atoms, as well as other electronic features like average local ionization energy, which has information about the electron density, just to name a few. And then we performed feature elimination. So I realize I'm running a bit out of time, so let me just hurry through. We then looked at the feature importance of using these machine learning models. So if we look at the transitions of going from large ions to small ions in each of these cases, we see that these changes are more influenced by the electronic features. So this is just a pie chart just showing the contribution of which of the features are more important. And then if we look at the complexes changing from smaller to larger ions, these are more influenced by the geometric features. So we can think about, if you have a larger cage and then you replace that ion with a small ion, you can think about then the chemical features become more important in trying to interact with the smaller ion. Versus if you have a smaller cage, you have a small ion replaced with a larger ion, there's going to be some strong repulsive behavior of this larger ion that is going to cause this smaller cage to try to expand. And so that's why this geometry is getting influenced here, we believe. Okay, so I'll wrap it up there. So we learned a lot about how ion size can dictate the coordination preference for these coordination environments. For example, the complexes that support potassium, which are large, also like ions that are similarly middle-sized sodium compared to the very small lithium. And the complexes that natively like the lithium prefer the middle-sized sodium more than really large potassium. And then changing from these large ions to smaller ions and vice versa have this positive correlation. And then the changing from sodium to either of these two other ions have an inverse correlation. We also identified a few particular complexes that are particularly amenable to potassium and sodium. Oh, sorry, this should be lithium over other ions. And we learned that the interaction energy is the dominant contributor for these differential binding energies. But to look at even greater resolution, a majority of that is coming from this electronic features for the going from the larger to smaller ions, and then the geometric features going from the small to smaller to larger ions. So with that, I'd like to thank a lot of the people who are involved in some of this work. So my postdoc advisor, Heather Kulik, as well as the group, as well as my funding from the Senate EFRC, it's a DOE EFRC. And with that, I'm happy to take any questions. I'm sorry that I'm running a little bit late. I have to actually leave exactly at 12. So I'm hoping I can answer at least a few questions before then.
Jake, go ahead.
Thanks. Yeah, really nice talk. I had a technical question that I'm kind of curious about. I'm guessing solvation effects are pretty tricky in DFT. How did you deal with that? How did you choose how many water layers were involved? And
yeah, that's a good question. So we use implicit solvent for this study because it's quite difficult to represent the full setup and how far to extend the water shell using explicit water, since they're DFT calculations, they're not cheap. But I will say we used a dielectric of 10 just to replicate a confined environment. So the bulk is 78, at interface is 1. So this is kind of a general standard for these confined environments. I think it comes from, I believe, the protein kind of scope field area. But yeah, that's why we didn't use explicit water shells.
Okay, thank you.
I think with this, we should probably. Why do I have an echo? Sorry. Yeah, we should just probably end the event. Thanks a lot for everybody. And we look to seeing all of you again in 3 weeks. So I'll still keep the event open in case you want to talk to the speakers or to network with one another. Unfortunately, I'll have to leave.